Okay, hello everyone, I'm Fab, I'm from NeverLocal, and today I'm talking about a library that we did. So this library is called T-Rust. What is T-Rust? It's a very small library that basically allows you to do one-time program using conjugate coding. I'll get to that in a second. It's written in Rust, that's why it's called T-Rust. It runs on TEs, that's why it's called T-Rust, and is no STD friendly, which means it can be used on embedded systems and microchips. Now, what this means in practice is that the library is like 200 lines of code, and the example folder, like the smallest thing, is like 3,000 lines of code. Sorry, but that's what putting these things on microchips means. It's terrible. Can be found at this link. So recap. First of all, what are one-time programs? They are programs that can be executed only once. That's why they're called one-time. They are useful for a lot of things, especially like in finance. You can imagine that a program that can be run just one time basically behaves like a resource. So you can put like a debt settlement scheme in it, and basically you can either pass it around or execute it and try to get the debt, basically. And if there is collateral, good. Otherwise, yeah, no good. But you can either try or try to sell it as it is. Then the nice thing is that these things cannot be done both classically and in quantum. And so now you may ask, what the fuck are we even doing here? And that is a very good question. But the thing is that if you have a secure enclave, like a TE, Trusted Execution Enclave, then you can do them. The problem is that no one likes TEs. Like if you ask a cryptographer, what do you like about TEs? They basically puke in a corner because they're terrible. So what we do is we try to minimize the trust required in the TE to run this thing. Okay, cool. So what is conjugate coding? It's a way to basically pack two classical bits into two quantum bits in a way so that you can recover only one. How do you do that? Basically, you encode the first bit in the Z basis, which is this, and the second bit in the X basis, that is this. So you have these two bits. You say, okay, if the first bit is 0, I put it, on the vertical axis, top. If it's 1, bottom. And for the second bit, you do the same. And then you scramble them, so you don't tell people which is which. You keep this order for yourself. You don't tell your friends. And then if your friends want to recover, say, the first bit, they do not know which bit they have to measure at Z basis. So they are forced to measure both in the Z basis. And then in doing that, they basically completely destroy the information coded in the other axis. So they destroy the other bit. At that point, you tell them the ordering, and they are happy because they can understand which one of the two measurements was noise and which one was actually useful. And they will need a TE to distinguish between the two. Like, I don't want to tell these people, oh yeah, what's your measurement? This one, okay, so this was the ordering, because at that point I may have just told them before. It would be useless. But if I put this thing in a TE, they can execute the measurements, give this stuff to the TE, and then the TE gives them, the bit string. So what does T-Rust do? Okay, it helps us building one-time programs, and the protocol is running in 3 phases. There is a preparation phase where the guy packing the information in the qubits sends you an encrypted program to be run on the TE. And then there is a measurement phase where you decide, which bit string you want to measure and perform the measurements accordingly on the qubits that you receive. You feed this stuff to the TE, and the TE computes if you have been a good boy or not. So in practice, this works like this. Preparation phase, I give you a table, which is incomplete, with some bits, and I give you a bit mask. These bit strings, and some of these entries are missing on purpose, will be encoded in the qubits, in the conjugate coding thing. Now, the bits that are present are called security bits. The other are secret bits, for reasons that I'll tell you later. And the bit mask keeps track of who's who. Okay, cool. Now, the TE also stores from the sending party an ordering thing that basically will tell you, for each couple of qubits, which qubit encodes which bit. So, for instance, here I'm saying bit string 0. Okay, whatever information is here will be encoded on qubit 0 because I have a 0 here. In here, I have swapped the qubits, and so it goes the other way around. So this is like the secret sauce that never has to come out of the TE, otherwise we cry. Okay, in code, this looks awful, like usually in code. It's a struct in Rust. We use these weird things here that basically keep track of how this thing is stored in memory. They nuke the memory to 0 after these things are, finished their use and lifetime, etc., etc. Basically, forget about all this. And yeah, so now measurement phase. Okay, you have this program in your TE. You're very happy, and now you want to actually execute it. So what you do is you take your program, you hash the input of the program, and that determines whatever measurements you have to perform. Now you take this input, so these bit strings of 0 and 1 hashed, and you perform the measurements using those bits as choices of bases. And you store this information in another struct, you feed it to the TE. And what happens is it's actually this. Basically, now you have two more things. Now I'm saying I measured in the X basis and I obtained 2 1s. I measured in the Z basis and I obtained 1 0. You feed this thing to the TE. The choices of bases basically determines which thing you want to measure in these bit strings. So 1 means I want this 1, and that's why this is grayed out. This is now destroyed for sure because of how conjugate coding works. So now TRust will fill this table. We'll use this information to verify that you did everything correctly. And this is what it looks in the end. It's basically saying, okay, these are your measurement outcomes. This was the ordering. This was the measurement choice, what you wanted. Using this information, it will basically cut out the noise in this couple and give you the other part of the thing. And it will write it here. It will do the same with everything, and it will write these numbers here, basically, in this row. Now you see that whenever I had the security bits, now I have 2 numbers. So what the TRust does, it checks that these 2 numbers are the same. This basically allows me to be sure that the TE wasn't fed with bullshit data. It was actually needed to come from the quantum measurement. Otherwise, there is no way to have these things here and here to be equal. There must be an error threshold because of how communication and noise and loss works in quantum computing. In quantum communication. But basically, you see, here is correct. Here is not correct. So this bit is stripping here, and we keep a counter. Basically, what we do is we count how many times these values do not agree. If it's too much, we gave the middle finger to the user and say, no, you're trying to cheat. Goodbye. Okay, cool. How do I use this thing? Basically, there are 2 ways. The first way is pure TE mode. Basically, you burn the program that you want to run one time in the TE with this stuff. Every bit is a security bit, and if enough bits aren't tripped, then it's good. Thank you. This is basically the first mode. The good thing is that it protects the TE better against replaying. It essentially makes it stateless. You don't need counters, hardware counters on the TE and stuff like that. Downside, if basically someone steals the root of trust of the TE, you are dead. Like the whole thing breaks down. Second way to use it is that you use the secret bits to check that you use the security bits to check that everything was done correctly, but now you use the secret bits, the one that basically weren't in the table in the first place, like this or this, to basically feed this secret stuff to another thing like a garbled circuit. So the good thing here is that if people steal the root of trust, we don't care too much. You literally need to steal the root of trust before performing the measurement. If you suspect that Intel stored the root of trust of the XGX before you use it, it's not a problem unless you literally collude with Intel. If they don't tell you what you have to measure, basically they cannot do anything. Downside is computation is lower because garbled circuits are slower. Okay, so you can play with this thing. It's open source. We provided plenty of examples. They can run on an ESP32C6 chip, which is $4. If you're short on money on QKD equipment, we also built an Arduino thing that basically simulates the quantum, the bit string, the measurement outcomes of this thing. The funny thing is that basically that thing is this thing. It's so small. Like this is the TE, This is the Arduino. You can play with it. Will it be secure? Fuck no, because there's no quantum, but at least it's fun. And it doesn't cost $20,000, which is good. Then announcement, basically we are going to demonstrate this thing for the first time with the actual QKD article tables and all the terrible thing that we need to do. It will go so bad. But basically, we will do it at this event that will be held in Naples in July. If you want, you should really come. The concert is no Tour Eiffel nor croissant, but there is Capri and pizza. So, I mean, we're trying our best. Yeah, that's it. Goodbye. Thank you very much. Questions?
I don't fully understand the timing of the root of trust attack. Like, if Intel, let's say, wants to use that as a real use case, or whatever, right? If someone has a root of trust before,
yes. So, the point is this. If you go to this table here, you see that in these rows, for instance, here and here, I do not store any information beforehand. I basically just tell you which qubit stored that information. So when you measure, you have this data here, but you never have this thing available whatsoever. So what that means is that as soon as you have a choice of outcomes, then you need to, this information is completely erased. In this case, this is not true. You have the 0 and you have the 1 on the TE. So afterwards, if you want to rerun this program and you have access to this secret information because you break the TE, you know how to unlock this thing because you have access to these columns. So now the point is, if I have the root of trust beforehand and I know the orderings of the qubits, then I can strategically measure. In this case, I can say, I measure the first thing in the Z basis, the second in the X basis, and now I'm able to fill both things with things that are not noise. So if I know the root of trust beforehand, I can do strategic measurements and recover both the classical bits. But the problem is that you don't just need to know the root of trust. You cannot just passively listen. You need to actively use this information to do the measurement. So, this is way more secure because even if you have this information, you have to convince whoever is operating the measuring equipment to do that for you. And then again, to make this usable, this information here in the empty things needs to be used to unlock a program which is not on the TE. The program will be like a garbled circuit, another thing, you feed these 3 secret bits in, and you are good to go. The problem is that because the quantum communications are noisy, you'll need to have some redundancy. Like for the garbled circuit approach, you will have these secret bit strings that will need to be error corrected in a way. They will need some redundant information in them. And that means a lot of headaches, which is why we are not doing that in the examples at the moment. There are some information theoretic things to be aware of. Done? Cool. Thank you.